My name is Masoud Olia, and I teach here at Wentworth Institute of Technology, and I'm back with another video, this time related to the topic of internal forces and moment. And my objective today is to show you how you can determine how shear load is going to change as a function of position. And in other words, I'm trying to show you how to find or how to plot the shear diagram. And then also from the shear diagram, I'm going to show you how moment is going to change as a function of position. And as you could see, this is a very simple example of what we call a simple supported beam or simply supported beam with just a uniform load covering about half of the beam with the intensity of 100 pounds per foot, and then a 300-pound concentrated load. And of course, the value of the shear, especially the value of the maximum shear and eventually the value of maximum moment, are important in design. When it comes to calculate the so-called transverse shear stress, we use the maximum shear load. And also we use the maximum moment to find the maximum bending stress. And that could be shown in another video later on. But anyways, let's get here. The first thing I want to do before I talk actually about the relation between the shear and moment and shear and the distributed load W and the relation between moment and shear, let me actually find the reactions for you. So this is something that you have seen, in your statics course where you have to calculate the external reaction. So here we have a pin at A. Notice that I didn't even bother to put the reaction developed in the x direction since I don't see any load in the x direction. So we only have a vertical reaction here and a vertical reaction obviously at the roller. So typically what you do, you take moment about either end. So let's say if you take moment about A and set it equal to 0, then we have the moment of RB, the reaction at the roller, about A, which would be times 12, and that's going positive counterclockwise. And then we have the moment of the 300 concentrated load times 9 feet. And then for the sake of finding the moment of this distributed load, we change it to a concentrated load. And you guys know that that would be the resultant load would be the area of this rectangle, which would be 600 pounds. Later on, I will erase this because I don't want you guys to get confused with that 600 pounds. This is only for the sake of finding the reaction at B and A. So we change that to a concentrated load, 600 right at the center through the centroid of the rectangle times 3 feet equals 0. So this should give me the reaction at B to come out to be about 375 pounds. And then obviously, if you just balance forces in the y direction or some forces in the y direction, since we have a 375 pound here for the reaction at B, and we have a total of 900, so this guy should take 525 pound. So this is just balancing, so you could just do it this way, RA plus RB minus 300 minus 600 of the forces that are going down. And since you already know RB is 375, RA then becomes 525 pounds. Okay, so we got the reactions, and that's the first thing we have to do. We have to figure out our reactions before we be able to do anything else. So what I'm going to do, let me just get rid of this right here, okay? Because remember, I just changed that to a concentrated load to find these reactions. So let me now show you how we can actually plot the shear diagram as a function of position and eventually moment diagram as a function of position. So the two important relations are written here for you. The derivative of the shear with respect to position is negative of the intensity of the load W, or basically this is called shear gradient. But when you rearrange this, dV or V becomes the integral of, so basically this becomes dV equal negative of the integral of dx, which actually what it means is that the net shear, so dV when it's integrated becomes the net shear. And you guys know that the graphical meaning of W the integral of W with respect to X, is the area under the W. Just be careful with the negative sign here. Net shear is negative of the area under W. This will allow us to draw the shear diagram. We'll do it in a minute. Then also, if you rearrange this equation and say moment or dm is equal to v dx and integrate both sides, this leads to this statement that says net moment, right, m2 minus m1 is equal to area under the shear load. Again, the integration means finding the area. So let me move over here and plot the shear diagram for you. So what I did here, I extended the line of action of each section down, and just remember that you need to always label your axes with the appropriate units. So shear load versus position, and position is in feet. So let's go ahead and draw our shear diagram. So I start with a concentrated load, the reaction here, which is 525. Whenever you see a concentrated load, just follow the direction of that load and go the magnitude of that load in the positive direction, in this case, 525. Okay, then the question is, after 6 feet, what is the value of the shear? So the way you figure that out is based on this statement here that says net shear is equal to area negative of the area under W. So the way I do it, the easy way is to just take the current value of the shear, 525, right? And now add negative of the area of the load. You see this, the area of this load, we did it a minute ago, is 600. So if you add negative of the area, that will give us the next value of the shear, which is minus 75. So that means that the value of the shear 6 feet later is going to be minus 75. Of course, I cannot do this to scale, but I'll do my best. So if this is 525, this is 75. Now, whenever the intensity of the load is constant, the shear changes linearly like this. Okay? Now, what happens after that? From here to here, nothing is changing, so the shear remains constant at minus 75. Then we see the 300 down, so that should bring us to minus 375. And then notice that this 375, negative 375, matches this 375. So we close the moment diagram. So that's our, close the shear diagram rather, sorry. So here we go. This is our shear diagram. And then later on we'll look at this and say, okay, what's the maximum shear? And clearly you could see that 525. But let me go ahead and draw the moment diagram for you now. Let's extend the point where, you see what happens here. Shear becomes 0 here. So we can extend that, and that's an important point actually. So let me do a little bit more extension so I can draw my moment diagram right below this. So this is again x in feet versus this time moment in units of pound-foot. Okay, let's go ahead and do this. Now, we need to know where shear becomes 0. So in other words, what is this? What is, I'm going to call it x actually. So let me show you. It's very easy to do this. There are different ways to do it. I'll show you later on by having actually the equation. Just take this triangle whose height is 525, whose base is unknown. I called it x. And just remember that the slope of this line is the intensity of the load, which is the 100, because the derivative of this guy is w. You see that dv dx is the negative of w. So it's actually negative of the slope, but the slope just a magnitude. So the slope of this guy is minus 100 because it's decreasing. So what is the slope? Rise over run. 525, rise over run x. That should be 100. Don't worry about the sign. So that becomes 5.25. So now I know this is 5.25. So let me go ahead and put 5.25 here. So if this is 5.25, this piece, a small piece that is hard to see, should be 6 minus 5.25 or 0.75. Okay. So now what do we do? Where do we go from here? What we do from here is that we know that the net moment is the area under the shear load. So we have to start at 0 moment, by the way. If you don't have any external moment here at this pin, you start at 0 and you have to end up at zero moment, unless if you have moment on those locations. Okay, so now what we have to do is to calculate the area of each segment under the shear diagram. So area is easy. This is a triangle whose height is 525, base is 5.25. So go ahead, find the area. This area comes out to be, let me just use a different color. So this area comes out to be half base times the height. So it's about 1,378.125. Then this is small area. First of all, it's negative. It's below. So that becomes very small, minus 28.125. So what I'm doing, actually, I'm calculating all these areas, and then I'll just go ahead and show you how this is done. This area here of rectangle is length times the width. So it's just 3 times minus 75, minus 225. And then finally, this area is 375 by 3. So that's 1125, also negative. Notice that actually if you add all the negative areas, that balances the positive area. And that's always the case in the absence of any external moment along the beam. Okay, we're ready to draw the moment diagram. So start at 0 here. Now keep adding the area. So if I'm at 0, I'm adding this area. That should put me at 1378.125. The question now is, how do you connect this point to the point, which happens to be actually the maximum moment? And the answer is that if your shear is linear, the moment actually is going to be a concave, it's a parabolic or second order. Or it could be either concave up or concave down. Now, the fact that the slope is negative is going to be concave down. So it's going to look like this. I can make a table here for you, just for your information. If this represents the shear and moment, if your shear is like that, decreasing linearly, the moment should be concave down. If the shear increasing linearly, it should be concave up. Okay, back here, where do we go from here? 1378.125. The next area is negative. If you add negative 28.125 to that, that will drop you to actually 1350. So just a little bit of drop because it's a small area. Continue with the concave down because it's the same slope, as you could see. So from here, add to 1350 a negative 225. 1350 minus 225 should put us exactly at 1125. So let's say this is 1125. But the question is, how do you connect? This time is going to be a straight line because you're integrating a constant. When you integrate a constant, the outcome is linear. And similarly, 1125 minus 1125, as expected, you got to get back to 0, but obviously with totally a different slope, higher slope. So that's your moment diagram. Notice that moment in this beam everywhere is positive. And the maximum moment, I can write it down here, the maximum moment happens to be 1378.125 pound-foot. And the maximum shear load, later on if you want to calculate the transverse shear stress, is 525. By the way, shear load, typically these numbers, we need just the absolute value to calculate the absolute bending stress or absolute transverse shear stress. Especially with the shear, we always look for the magnitude. The sign is not important. Now, one last thing before we are done with this video is that since the moment everywhere is positive, you guys remember we used the analogy that a positive moment is one that causes the beam to be in tension in the bottom fiber and compression in the top fiber. So this is the positive moment. Negative moment is just the opposite. So the beam would bend like that. So the top fiber is in tension. Here it was in compression, tension, tension, compression. And you guys remember in the before I had shown you that this analogy is used with the happy face, sad face kind of. So happy is this mouth, which means the moment is positive. Just a way to remember things. And sad means negative moment. And that's the shape of the mouth. So that analogy could be useful here. Of course, This is everywhere is positive, which means this beam cannot be sad. If you show the elastic curve of this beam should bend, like this. So you see the top fiber is always in compression, the bottom fiber is always in tension, and that resembles the happy face. And that's the way it should be, because you see the moment everywhere is positive. I want to come back and show you how you can find actually the equation of the shear and moment, especially in this section of the beam where we have this distributed load. So we're going to take a pause, erase this, and come back and show you the equations. Okay, now that we erased the equations that we had here, I left the diagram here for you. So this was the shear and bending moment diagram for this simple beam, simple supported beam with a very easy type of loading here, a uniform load and a concentrated load. Now I want to show you how the shear and moment they change, or I want to get the equation of the shear and moment, equation of this straight line and equation of this parabola. And there are two ways that you can do that. And of course, I want to do this only over 6 feet of this beam. In other words, from here, from A to where this load ends. So if you take this to be our X from here. Okay, the equation can be determined by two methods. The first method I want to show you is by simple integration. So integration is an easy method where you just say, okay, my distributed load here is 100 pounds per foot, is a constant, right? And we know that V is the integral of negative of the integral of W. So if we go ahead and put the 100 here instead of W and integrate this, that becomes minus 100x plus a constant of integration, which I call it C1. That constant of integration can be determined based on what we call a boundary condition. The obvious boundary condition, as you could see, is that at x equals 0, here x equals 0, the shear load is 525. That's always actually the reaction at that point. So boundary condition at x equals 0, shear is 525. If you set x equals 0 here, right, and shear equals 525, clearly C1 becomes 525. So I'll come back and I say, oh, my shear as a function of position is minus 100x plus 525. That's easy. We determine the equation of the shear. Actually, that's the equation of this straight line. And now, if you wanted to know when shear is 0, just set shear equals 0 and solve for x. So you see x becomes 525 over 100, which is the 5.25 that I found earlier for you. So if you have the equation, you can set the shear equals 0. All right, what about moment? Okay, go ahead and integrate one more time, because moment is the integral of V. So if you go ahead and integrate V, which is minus 100x plus 525, then moment becomes minus 50x squared plus 525x plus a constant of integration C2. But C2 this time happens to be 0, because at x equals 0, moment is 0. So that's the boundary condition we have for moment. So this means your constant of integration would be 0. So therefore, your moment equation becomes minus 500x squared plus 525x plus a 0. So this is a moment equation. This is the shear equation, only valid between 0 to 6, between 0 to 6, over which the load is acting. Now, let me show you totally a different approach that you could get exactly the same two equations. Okay? This approach is based on what we call an equilibrium approach, where we would cut the beam and actually try to find the equation of the shear and moment based on the equilibrium equation. So somewhere between where this load is acting, between A and the end of the load, cut the beam. And just draw the free body diagram of that. So we know that we are cutting this at some arbitrary location, x. So this is our x. And remember, we have a reaction at the pin, which we calculated to be 525. Now, just one thing to remember is that once you try to show the internal forces here, your shear load has to be down and your moment has to be counterclockwise. These are the positive sign convention for shear and moment, and you have to stick with that. Let me call this point just point O. Okay, so, and remember, this is a constant intensity of 100 pounds per foot. So my objective is to find V and M, and they have to match exactly what I have here, these internal shear and internal moment. So what does equilibrium mean? It means just apply the equilibrium equation, like sum of the forces in Y equals 0. So balancing forces in the Y, we have minus V, we have a 525 going up. So remember, for the sake of finding now the force here, I'm going to change this to just a concentrated load of the area of this rectangle, 100 times x. And I put it right in the middle at x over 2 from this end or the other end. So that would be a minus 100x. And guess what? When you solve for V, you get exactly the same equation. Matching. There we go. Totally different approach. This was by integration. This is by equilibrium. All right, but what moment? Well, another equilibrium equation. Take moment about O. Say it equal to 0. Counterclockwise positive. Just as a reference. So start with this internal moment M. Obviously, shear is right at O, doesn't have any moment. 525 does, going negative. 525 times x, right? And then what about the 100x? That's going to have actually a positive moment, 100x times x over 2, right? 100x times x over 2 equals 0. And as expected, of course, when you clean this up, this becomes minus 50 x squared plus 525 x. And that's the equation of the moment as a function of position. So of course, this is the equation of this parabola here, and this is the equation of this straight line here. So I hope you enjoyed this video, and hopefully come back with more examples of shear bending moment diagram, of maybe more complicated type of loading, especially loading that are not constant, and maybe they're changing linearly in the shape of a triangle. Okay, thanks for watching and listening.